Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on control systems theory. This is a lecture series where we do simulations of control systems in MATLAB. So I use MATLAB 2007 for this purpose. And today, previously we have talked about simulation of full state feedback systems using MATLAB, and we have also talked about simulation of dynamic compensator based systems using Leuenberger observer and pole placement controller with MATLAB. And now we are going to discuss the integral control in state space from the simulation point of view. So we are going to simulate an integral control state space system in MATLAB. So let's get started. First of all, let's select the tutorials folder as the drive folder, as the target folder for MATLAB programs that we are going to write today. So I will just click here and get the new file. And let me create a function file, because as we know, in order to implement a state space system, we need to create a MATLAB function. Dx equals ss model 2. I can name this function anything, but I'm just going to name it ss model 2, which means state space model 2, because we already have discussed one model before and this is our second model. So the input to the function is time and state t and x, and the output is dx. So we save this with the same name as the function name, ss model 2, and now we need to tell the MATLAB what is the A matrix in the system. So before we go there, let me refer to this PowerPoint presentation of 2 slides which I have prepared for you. So consider the following single input single output system. G of s equal 1 over s cube plus 2s square minus 3s plus 4. So this is a third order transfer function, and you can see that if this is a transfer function of some plant, then that plant is unstable by Routh-Hurwitz criteria, because first of all the coefficients of the denominator are not of the same sign. So without even going into the Routh-Hurwitz table, we can tell that this system cannot be asymptotically stable. So we convert this system into state space using the technique that we have learned in the linear control systems course. And in this corresponding state space model, we have this A matrix where there is all zeros except ones above the main diagonal, and the coefficient of the denominator of transfer function come in the last row of the A matrix with opposite signs and reverse order. B matrix is 0 0 all ones, and Y will always be will have the coefficients of the numerator. In this case, numerator is just 1, so we have the numerator coefficient here, and the rest of the matrix will be filled with zeros. Okay, if you want to know the detail of conversion of transfer function to state space, I recommend that you go to the linear control systems course review lecture part 1. Okay, so let me tell you something very important here, that whenever you convert a system from transfer function to a state space, then that state space model is always controllable and observable. You don't have to check the controllability or observability of this state space model if there is no pole zero cancellation in the transfer function. In this case, there is no zero in the transfer function, so obviously this transfer function is irreducible. If the transfer function is irreducible, which means that if there are no pole zero cancellations in the transfer function, then the conversion of transfer function into state space always results in controllable and observable state space representation. The reason for that is that transfer function is only capable of representing the controllable and observable part of the system. And when you convert a system model from transfer function to state space, the state space is always controllable and observable, because this this is only the controllable and observable part of the system, or maybe this system is actually controllable and observable if this model is complete. So so we don't need to check observability and controllability, but if you still insist, you can check the determinant of Q matrix, it will be -1, and the determinant of O matrix, it will be 1. Both are non-zero, so system is controllable and observable. Let us write the program for this system. So we have A matrix for this system as 0 1 0 0 0 1 and -4 3 and -2, and the B matrix is 0 0 1, and B is a column matrix. And so we have told MATLAB about A and B matrices. We can also design a controller. Let me copy A and B matrices, Control C, and then place those A and B matrices here, press enter. So A and B are created, A and B matrices are created in this command window. So I use the command place K equal place A comma B, and let's place the closed loop eigenvalue at -1 -2 -3. You can place them anywhere, but in this case, because it is a single input system, you cannot place the eigenvalues on repeated, so you cannot have repeated eigenvalues here. Like for example, if I say -1 -1 and 3, then it will give me an error, can't place poles with multiplicity greater than the rank of B. And so that's one thing, important thing to know. But I changed the pole locations to -1 -2 -3, so this gives me the gain 2 14 and 4. So I tell the MATLAB that my gain is 2 14 and 4, and then U equal -k times x, and then dx equal A times x plus B times U. That completes my, I save this file, and now I have to create a new script file. CLC means clear anything on the command window. So far on the command window we have all this written here, so CLC will clear all that, and clear all, it will clear the previously defined variables. And then there is one more command you can use, close all. So this will close any previously opened figure windows or any other windows that you have opened that are not to be used by this program. So we t comma x is equal to ODE 45 at SS model 2 comma 0 to, let's say, 15 seconds, and give the initial conditions, let's say 7 -3 and 4. Maybe you can give any initial conditions, does not matter much unless you are trying to simulate with specific initial conditions. So let's have plot t comma x, and we can also have the legend. So we can also add legend. So in this case we have 3 state variables, so we add 3 legends, x1 x2 and x3. And now we save this file and we call this ss model 2 underscore s, just to emphasize that this is a script file which calls the function ss model 2. click on save and we run this file, and there is an error here. Maybe I have not done something right. So unbalanced or unexpected parentheses or brackets. I go back and I see here that there is this bracket that should not be there, and I run again, and this time no error. So that's your system. I can also have the grid on, so you can see here that the system is asymptotically stable, everything good as before we did for the previous system. Let me just grid on, run it again, and now you can see with the grid that all the three states are converging to 0. But now let me just try to add. So since here, if I go back to the state space model, y is equal to x1. So since y is equal to x1, what I will do is I will add x desire equal so it will be, let's say 1 0 0. So I want x1 to go to 1, and then my control becomes minus k x minus x desired. So let's see if this system tracks the step input. So since this is a constant input, so it is a unit step because it's 1. I can make it any constant value. So you can see here that there is a steady state. X1 actually is converging to some value, but this value is not exactly equal to 1. Actually the x1 is converging to 0.3334, and there is a steady state error. So we wish to remove the steady state error from the state space. So coming back to this slide, see, this system is type 0 system because there is no pole at the origin for the open loop system. And if you do not use integral control for this system, type 0 system has non-zero steady state error with respect to step, which we are looking at right here. So this system has a non-zero steady state error with respect to step. So how do we incorporate how do we remove this steady state error? By using the integral control. How do we use integral control in state space? We have to define a new state variable, in this case x4. x4 is the integral of the difference between output and the desirable value of the output. So this gives us x4 dot equal y minus y desire. In our case, y is equal to x1 and y desire is some value which is the desirable value of x1. So if we incorporate this fourth state into the system, our system becomes 4 cross 4 or fourth order system, in which the third order system stays the same as before. The fourth column and the fourth row is added in the A matrix, where x4 dot is 1 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 plus 0 times u and minus 1 times y desire. So there is a new input in the system, and y is equal to 1 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4. This is how you augment the system. This is called augmenting the system with the integrator state. So this is the integral, this is a system with integrator state, and now we can implement the integral control based on this system. How do we do that? We just make the state space like this, convert the state space into this format, and then you will see that the steady state error will be removed. We go back to the model, we make the A matrix 4 cross 4 by adding additional zeros, and final row 1 0 0 and 0. So this is 4 cross 4 A matrix, and this is 4 cross 1 B matrix, and now we have to recompute the control gain. So we copy the A and B matrices, we go to the command window, we paste them, and then I can use the up arrow key to browse through my previous commands. So here is my one of the previous commands. So now my system is fourth order, so I have to select 4 poles. So let's suppose I choose one pole at let's say minus 1.5. okay, I can choose it anywhere. So here is my control gain: 18.5, 23, 5.5 and 9. So my new control gain is 18.5, 23 and what was that, 5.5 and 9. So I go there, so this become 5.5 and 9. So this is my new control gain, and my desirable value will be, so since I have 4 states and I want state 1 to go to the value 1, this is now my new state space system, which is 4th order system. I have made A matrix 4 by 4, B matrix 4 by 4, and I did not check the controllability before placing the poles because well, adding an integral state does not well, you still can check the controllability unless you have some theoretical result which tells you that, you know, adding the integrator state will not affect the controllability of the system. Okay, so I also have to add the initial condition for the integrator state. I add 0 initial condition for it, which is the best possible initial condition for for integrator state. And now since I have 4 states, I will go to x4 in the legend. So now I have the integrator states, and now look at my desirable value for the x1, it is 1. So what I am expecting now is that when I run the model, x1 will exactly go to the value 1 in steady state. There will be no steady state error. So I run this system, and here it is. The x1 state in blue, it's actually going to 0. I have to see why this is happening. All right, so x minus x desired, and then oh, okay, got it. Actually, I have to write the system in this form in the program. So what I will have is, instead of x desire, I will have simple y desire. So what I will do is, this is y desire. Let's suppose y desire will be a scalar, so let's suppose it has value 1, and u is simple minus k into x, but we have here plus this vector 0 0 0 minus 1 times y desire, as we have on the slides. You can see here that on the slides we have 0 0 0 minus 1 times y desire. We put the same matrix here, and now we save this file and we run this file. Alright, we go to the script file and we run this file, and now you can see here that the state x1, it goes exactly to the y desired or x1 desire. So we gave it desirable value equal 1, so it goes exactly to the value 1. So there is the steady state error has been removed with the help of integrator state. So these are the dynamics of the integrator states. So integrator state is something, a variable that has been introduced into the system for calculation purposes only. This variable does not have any effect on the physical response of the system. The physical response of the system is determined only by the trajectories of x1, x2 and x3, because only x1, x2, x3 are the actual states of the system. So this system is still asymptotically stable and it is tracking the step commands with zero steady state error, and this is the integrator state. It just for calculation purposes, it has no effect on the dynamics. It does not represent the dynamics of the systems. It represents how the value of the integral of output minus the desired value of output behaves. And so we can also give some other desirable values. So for example, if we want to track the value 5, let's see y desire equal 5. So we save this file, Control S, and we run the model, and now you can see here that x1, the blue line, it is tracking the value 5. So we can achieve the desirable value of x1 using this integral control with zero steady state error. All the other states are going to 0, and because we are only interested in tracking the step command with output. So let's suppose we want to track some negative value, say -3 or say -2, Control S, and then we run this file, and you can see here that the -2 value is tracked. So similarly, you can track any positive or negative constant value using this system. So this was the lecture which was intended to demonstrate integral control to you. Hopefully you understand the concept of implementation of integral control in state space with the help of this lecture. If you have any comments or concerns, please let me know. Next time I will show you how you can add observer to this system as well. So we have seen how we add observer into the system previously, SS model 1. This was the system where we run in the previous lectures, but in this lecture we developed the integral control based state space system, and we saw how the steady state error was removed. Let me show you the figure again. So here we are tracking the value -2. x1 is our output of the system, which is having zero steady state error. Thank you for watching.